Back again. This is Stripe. Today you got notes for section 2.3, uncertainty in data, objectives, some of the things you ought to know how to do as we get done with this section. You need to understand about accuracy and precision, what they are, differences. You need to be able to figure error and percent error. And you need to work with sig figs and make sure we report all of our answers to proper number of significant figures. Review, experiment, set of controlled observations that test a hypothesis. Got a few new vocab terms you'll be getting. And measurements, our main idea, measurements contain uncertainties that affect how a result is presented. Here's your definitions for accuracy and precision. Very closely related terms, but a little bit different. Accuracy is talking about how close it is to an accepted value. Down here in this little chart at the bottom, see, it's in your textbook also. But if it's accurate, it's going to be on the target. So like this one is accurate. It's hitting the target. Precise, how close measurements are to one another. Also we'll refer to their number of decimal places we can report. But like we can be precise, very close together, but not very accurate. Not very accurate. Over here they're spread out a little bit, but they're all fairly close to the target, so we can, or they're all close to the target, so we consider that accurate and precise. Over here, they're awful spread out, and none of them are very close to target, so we consider that not accurate or precise. But we actually can, in the lab, you can get some values that are completely, every one of your trials, every one of your experiments is way off, but when you average them together, you get about the right answer. So in a sense, that could be considered not very precise, but accurate. But generally, if they aren't precise, we're not going to consider them accurate. Error, different, another one of your vocab terms, the difference between an experimental value and the accepted value. So, very key little idea. This little chart here, it gives us our accepted value up here is 1.59, and then 3 different students did an experiment calculating density, or measuring density, and you see their errors. Generally, when we look at the accuracy, we just look at the final result. So in this case, that's the most accurate. So that's very accurate. Where over here, precision, we look at the individual trials, and this one's very precise. Much more precise than the one that turned out to be accurate. Yeah, the one that was accurate was all reasonably close on it, but ideally we want them to be as precise as student C and as accurate as student A. But if you're getting precise, it can be the more important actually than the accuracy, because that means at least you're doing the same thing all the time. It's usually easy to fix if you've got some errors there. Percent error, another key. And there's our formula for percent error. I usually leave this times 100 off of there. This gets a little confusing. When we divide, you times 100 to move your decimal place twice. This is easy to look at your calculator, move your decimal place twice and do it. But when we start trying to manipulate the formula, if you get that times 100 in there, it just gets messy. Significant figures, something we're going to do a lot of work with. Let's call them sig figs. All known digits plus one estimated digit. Down here, with an example, using a ruler to measure. We know this thing is 5 centimeters. Obviously 5 centimeters, between 5 and 6, so that's known. We can say it's between the second and third mark. So we know it's 0.2. Then we know somewhere in between there, and this person's going to say it's 0.03. So this one's saying it's 5.23 centimeters. The 3 is estimated. Somebody else might have thought it was 5.22. Somebody else might have thought 5.24. All of these would be good measurements. Now, if you just had 5.29, wouldn't have been very good because obviously it's not that close to there. But we can have differences, error in that estimated thing. So difference is a better term than error. Yeah, it's not wrong. So we can see some variations there, and that's okay. And here's our rules to tell the sig fig. All non-zero digits are always significant. Zeros between non-zero numbers are always significant. I call these trapped zeros. If they're trapped between two non-zero numbers, are significant. So it's the zeros that we have to figure out. Now, if they're all final zeros to the right or decimal, are significant. So if you got a decimal number and you got some zeros out there at the end, we consider those significant. Rule 4 is telling us the ones that are not significant. And there's two cases here. They're calling them placeholder zeros. We might see things like 0.000 and then start seeing some numbers. These zeros are not significant. And so on the little tiny numbers, those starting zeros are. On bigger numbers like 3, 6, and if we have a bunch of zeros, all those zeros are not considered significant. If we want to make some of them significant, we're going to rewrite it in scientific notation. Then rule 5, counting numbers and constants have an infinite number of significant digits. Rounding numbers. Calculators don't get sig figs. So you put a bunch of numbers in your calculator, you might get a whole big long answer on your display. Now, our base rule here is answers will never have any more significant digits than what we started with. So that's our base rule. We'll get a little more specific with this as we go around. Well, rules here for rounding. We're going to continue to use the same basic rules. They got a little bit of extra in here, and you'll see it in some science textbooks. So occasionally we may be slightly different on our answers than the textbook would be. But if the digit to the right of the last sig fig is less than 5, don't change it. If it's greater than 5, round it up. Where I'm going to be different here, they're rule 3. If it is 5, sometimes they're saying you round it up, sometimes you don't. We're always going to go up. But you may get to future class, whether it be in college. Yeah, or you might get a professor that gets real picky with this. But it really doesn't make mathematical sense, but it pops up in a lot of science textbooks. So there's a continuation of that last rule. So we're just always going to round up for 5. It makes more sense. And then when we add and subtract, our sig fig rules are, we work with the decimal places. So you round the answer the same number of decimal places as the ones that had fewest decimal places. With multiplication and division, we work with sig figs. And we look at the fewest sig figs. We'll be very frequently talking about this. The addition, multiplication, divisions, when we end up using the most stuff, we don't really end up doing that much addition and subtraction in chemistry. Some, but we do a lot of multiplication, division. So, find the number of sig figs in each of the following. Okay. So, I think we got our answer there, but if we look at the first one, it's got 2, because just the 2 and the 8. Those trailing zeros on a big number like that, not significant. Here, they're all significant, because that 0.0 after the decimal when we get considered significant. Here, these leading zeros, not significant, so it only had 1. So that's why the 2, 4, 1. You should get very good at identifying the number of sig figs. What's the percent error? So first we got to figure out the error. So we did 2.00 minus 1.80. Now it really doesn't matter which way you subtract that. I always just pick the big one minus the small one because positive, negative doesn't matter. So that gives us 0.2. Then you divide by the accepted value, which in this case was 2. So 0.2 divided by 2, same as 0.1 divided by 1, which is same as 0.1, 0.1, which is 10%. So if you weren't able to figure that one out, that's how you would have done it. Or you could have taken your calculator, did 0.2 divided by 2, you got the 1. So that's 2.3. That's all for now.